Last class we saw fission, and we said fission is division. A generally large nucleus gets split. But there's another side to nuclear chemistry, and that's fusion. So fission is division, and fusion is coming together, fusing together. So we generally see two small isotopes being squished together, forced together. Now, most importantly, that happens in the sun. The sun is so massive, the gravity is so large, that the atoms at the inner core are being forced together. So the sun is mostly made of hydrogen and helium, two very small isotopes. And those small isotopes are squished together and turned into larger ones. And different sized stars throughout the universe, the same process happens over and over again. Smaller isotopes are forced together to form larger isotopes, and then those larger ones are also forced together to make even larger ones. Eventually, the star becomes unstable and blows up. Now, all of those new elements that were created in the core of the star are scattered across the universe, where chances are they're going to get together and make a planet. And just like that, humanity. So fusion is the forcing together of these isotopes. Here we see two small hydrogens, two isotopes of hydrogen, hydrogen 2 and hydrogen 3. Now on their own, they don't want to get together. Those nuclei are going to repel each other because they're both positive. But if enough energy is provided to them, they will go together. And you see, in this case, from the fusion of these two hydrogens, we get helium, a neutron, and then a lot of energy. Now, right now, our nuclear reactors are all fission reactors. The problem with a fission reactor is the leftover stuff is very radioactive. And it's very radioactive for thousands and thousands of years. So after we derive the fuel from fission, we have to find somewhere to put the leftovers. And that's problematic. Our best answer is to put it underground in some kind of bunker. But with the materials lasting thousands of years, and a bunker only lasting decades, that means we have to keep moving it every few decades. So fission reactors are problematic. Now there's a quest to make a fusion reactor. If we have a fusion reactor, it would have unlimited energy, and the byproducts would be 100% clean. You see the reaction pictured. If we put together hydrogen and only get helium out of it, well, there's nothing radioactive about helium. Now the problem is, in order to make a fusion reaction happen, we have to get it to really, really high temperatures. Now, we're able to do that, but only at a very small scale. And the energy that we have to put in to heat it up is less than the energy we get out of the fusion. And right now we can only do it at a really small scale, and so we can't do enough to use it as an energy source. But if we ever figure it out, we will have unlimited clean energy. And I don't mean clean energy in the sense that solar panels or wind energy, because those are cleaner, but they're not really clean. Fusion would be 100% clean and would solve a lot of problems in the world. Right now, there's several places and people working on it, spending billions of dollars. Korea, Russia, United States, they have been working on this for some time. But the problems, the hurdles to overcome are pretty large.